So this video is going to go over some drugs used to treat Parkinsonianism, which can arise either from natural destruction of the dopaminergic neurons in the substantia nigra. It can also be drug-induced as well. So here's sort of a diagrammatic representation of what's going on in Parkinson's. Illustrated here are 3 separate neurons in 2 separate areas of the brain. You can see here the GABAergic neurons, and these are sort of the main output that's going to impact motor function, and they're contained within the corpus striatum. Alongside them in the corpus striatum are the acetylcholinergic neurons. There's additional input coming from dopaminergic neurons, but those are cell bodies located in the substantia nigra, and that's exactly what's affected in Parkinson's. So in someone like our PBL patient, we're still going to have the GABA, we're still going to have the ACH. And that's going out to motor function. But we have a destruction of the dopaminergic neurons arising from the substantia nigra, and that's putting an imbalance in the acetylcholine, causing increased function, and that's going to end up affecting the motor function. And so this kind of illustrates exactly what we're going to try to do to treat this. We can do this from sort of 2 different philosophies. One is because we have that dopamine loss, we can try to increase this. And we would do that by means of dopamine agonists. Because we have lost those neurons, and so we're going to either try to increase the dopamine, or the other option is we can decrease acetylcholine, and we would do that by means of anti-muscarinic drugs. So this kind of illustrates, again, the 2 kind of main strategies for treating Parkinson's. All right, so I'm going to start by talking about the antimuscarinic drugs, because there's not really a whole lot of information you need to convey. So again, they're working by decreasing excitatory actions of cholinergic neurons on cells in the striatum. Green being good, let's kind of go over a couple of things that they do. So they can help improve the tremor, and they can also help to improve the rigidity. But they're not so good at alleviating the bradykinesia. And for this reason, these are really used adjunctively with the dopamine strategy that I mentioned in the previous slide. So let's go ahead and start talking about that, because there's a little bit more information. All right, so I'll start off by talking about a couple things first that not really acting in the periphery, but are kind of moving into the periphery, and then there's different actions once you actually get into the brain. So I've illustrated the blood-brain barrier here in blue. So everything down here is in the periphery. And so one thing you can do is give levodopa. So you're just increasing L-dopa, and that's one main strategy. You can't give straight up dopamine because its bioavailability is really poor and it doesn't cross the blood-brain barrier, but L-dopa does. And then there's also other drugs that are going to decrease the degradation in the periphery, which will kind of increase our serum concentrations. So they're drugs that act on COMT, which degrades L-dopa, as well as dopa decarboxylase. And so these drugs are normally given in conjunction with L-dopa to sort of increase that bioavailability as best it can. So next we're kind of move into the brain and talk about the different drugs that work there. So once we have that L-dopa that's now moved into the brain, 2 things we're going to try to do is, just for starters, try to increase the dopamine levels by decreasing their degradation. So the first way to do that is by using a monoamine oxidase inhibitor. And so that's going to decrease dopamine degradation by this enzyme. And some drugs that do that are selegiline and rasagiline. So again, these are monoamine oxidase inhibitors. And by themselves, they don't really do a whole lot, but again, they're used adjunctly, so they're going to be given with L-dopa. On this side, we also have another enzyme, catechol O-methyltransferase, which is going to degrade dopamine in the brain, and some drugs exist to do that. So this one's called entacapone, and that's decreasing the degradation, again, by inhibiting catechol O-methyltransferase. And by itself, It's really not worth a whole lot, but given with L-DOPA, using adjunctively, we can increase the availability of L-DOPA and thus the dopamine levels within the brain. So in the next slide, I'm going to talk about the drugs that kind of act on the receptors. So to kind of round this all off, I'm talk about some drugs that agonize the receptors or increase the effect of dopamine on the receptors. So these are dopamine agonists. And I kind of have them separated mainly because pramipexole affects on the D3 and bromocriptine, and ropinirole work more on D2. Apomorphine is really not selective, one versus the other. So talk about each one of them individually real quick. Bromocriptine, it's an ergot derivative, so it's an alkaloid. It's the main active part of LSD, and it increases the functional activity of the dopamine receptor. Pramipexole over here is non-ergot derived, but acts mainly on D3, and it's effective monotherapy in mild Parkinsonism, and can be used with L-DOPA in more advanced disease. So it's administered orally 3 times daily, and excreted largely unchanged in the urine. Ropinirole, it's a D2, effective monotherapy, but can be used with L-DOPA as well. Standard form is 3 times daily, but you can also have a prolonged release form. And apomorphine, it's a potent receptor agonist. It's interesting because it's injected subcutaneously and can provide rapid, like even within 10 minutes, but only works for like an hour or two. So I think that kind of wraps it up.